Hello everyone. Today I will present our work, VideoAuto-R1. This work shows that chain of thought answering is not always better than direct answering for video understanding. Therefore, VideoAuto-R1 adopts a reason when necessary strategy. It first produces a direct answer, then adaptively invokes chain of thought when needed, and finally provides a reviewed answer. This is joint work with KAUST, Meta, and Princeton University. Chain of thought reasoning has pushed large language models to new heights by following a think then answer paradigm. However, unlike standard math reasoning, video understanding relies heavily on visual perception rather than explicit step by step reasoning. Therefore, a natural question arises: when is video chain of thought actually necessary, and how does it compare with direct answering? To answer this question, we first analyze existing video reasoning models. Our first finding is quite surprising. On many video benchmarks, COT actually performs worse than direct answering, even though it produces much longer response. Our second finding is that COT gains mainly appear on math-related video benchmarks. So why does COT sometimes hurt video understanding? We find that many video questions are perception dominant. In these cases, the model may already have enough evidence to answer directly. Forcing it to generate long reasoning can amplify visual ambiguity and lead to overthinking. The key takeaway is longer reasoning does not necessarily mean higher accuracy for videos. Therefore, instead of always using COT, we want the model to reason only when necessary. This motivates our method, VideoAuto-R1, which enables efficient video auto thinking. Concretely, we propose an answer twice, think once mechanism with dedicated designs for both training and inference. First, we design a novel output format: answer, then think, then answer. The model first gives an initial answer, then performs reasoning, and finally gives a review answer. This format is guided by a carefully designed system prompt. For training, we use a dual answer reward with GRPO. The task reward optimizes both the first answer and the reviewed answer. We assign a larger weight to the reviewed answer because it serves as a final prediction. Meanwhile, we introduce a fallback mechanism to discourage spurious initial guesses and reward honest uncertainty when the model cannot answer immediately. During inference, we use a confidence-based early exit strategy. The model first generates only the initial answer. Then we compute a length-normalized confidence score based on the log probability of the generated answer tokens. If the answer is higher than a threshold, the model exits early and directly uses the initial answer. Otherwise, the model continues decoding, generates the reasoning process, and then outputs the reviewed answer. Now, let's look at the main result on video QA benchmarks. VideoAuto-R1 surpasses the Quinn baseline and achieves state-of-the-art performance on several video QA benchmarks. More importantly, it achieves these improvements with much shorter responses. For example, compared with always using COT, VideoAuto-R1 significantly reduces the average response length. The think ratio is also adaptive. On perception-oriented benchmarks, the model reasons less often. On reasoning-heavy benchmarks, it reasons more often. This shows that the model learns to allocate reasoning effort based on question difficulty. It also generalizes well to the temporal grounding benchmarks and image reasoning benchmarks. We further compare different training strategies using the same data. We find that SFT can perform competitively with standard RL, while RL is particularly helpful for grounding tasks. Our VideoAuto-R1 achieves a better balance between the performance and efficiency. This supports our main argument. For video understanding, adaptive reasoning is better than always reasoning. Compared with training-based thinking mode selection, ours requires less data effort and provides more stable improvements. Here, we show two examples. On the left, the question is an easy perception question. The model only needs to recognize the main action in the video. VideoAuto-R1 gives a confident initial answer, so it exits early without generating COT. This saves computation and avoids unnecessary reasoning. On the right, the question requires more complex reasoning. The initial confidence is low, so the model continues to reason. After the reasoning process, it produces the correct reviewed answer. Thank you for listening. You can find more details on our project page.